All right. Good afternoon, everyone. I think it's time to start. So our homework one, I believe, will be due on next Friday. So if you haven't started, so please start right now. Don't try to rush at the final minutes. Right? And also, please leverage the office hours. And we're happy to provide any kind of help. Okay. Okay, so let us continue with the definite theory. At the end of our last lecture, we introduced the concept of exchangeability and the associated definite theory. So definite theory is very fundamental and it's very critical. Well, you can will it as a rigorous and mathematical justification of the rationality of Bayesian modeling. Right? Remember, the philosophy of Bayesian modeling is that, okay, I'm gonna view all the unknown parameters of interest as random variable, right? And whatever parameters we assume, okay, it was first generated from some wire distribution. Given that parameters, we generate the next level of next level random variables. And if we have observed the values of random variables, and given those observations, we try to infer the posterior distribution about these unknown or latent parameter values. That's the idea of Bayesian modeling, right? So, although it seems like just a philosophical choice, right? We talked about the idea of frequentist point of view, just consider the parameter value as some fixed unknown constant. There's no randomness. You come out all kinds of estimator to approximate, right? But we do have some theory to justify the correctness of such modeling philosophy. That is the definite theory. Okay? So it is based on assumption that your random variables of interest are exchangeable. So exchangeable is a much weaker assumption than the IED assumption. So it is applied very widely in Bayesian modeling because IED, we know that is very strong, right? You assume all those random variables are independent and identically distributed. And if you adopt the assumption that those random variables of interest are just exchangeable, it just requires some symmetry in the probability density. Remember, the exchangeability just asked us, okay, if this n random variables, they take the set of values x1 to xn, you just permute the values. The joint probability doesn't change. That's the exchangeability. So exchangeability is a very widely used assumption. It's much more flexible and expressive than IED assumption. And based on this widely used assumption of your random variables, definite theory tells us the joint distribution of those exchangeable random variables, their internal structure reflects a Bayesian sampling procedure. Right? So specifically, if we consider an infinite number of binary variables, x1, x2 to x infinity, right? So if they are exchangeable, then there must exist a distribution. Right? So F here is the cumulative density function of that distribution on 0, 1, meaning that the range is between 0 and 1. And given such distribution F, we can claim that for any n, meaning that you can pick up any subset of random variables from the sequence, we have the joint probability of these n random variables expressed in this form. So this is actually an integral, right? From 0 to 1, and the integrand is this guy, theta to the power of Tn, 1 minus theta to the power of n minus Tn, and this derivative of this cumulative density function. And we know that derivative of a cumulative density function essentially is is actually the probability density function over theta, right? So you can see that this is essentially a marginalization over this intermediate random variable theta or latent random variable theta. Mm-hmm. No, it's just about a binary. Yeah.
Then the generalized is just the average.
Average of what?
Average of posterior.
No, there is no posterior here. We're not talking about any posterior.
If you consider it as a prior, yeah, then theta to the Tn 1 minus theta to the n minus Tn is posterior.
No. This is we haven't talked about how to leverage this distribution to, for example, if you assign a prior distribution in this way, and if you have observed T1 to T3, T5 until like T100, how do you calculate posterior distribution? We just talk about their joint distribution.
I know I said that it is sometimes can be integrated.
No, I don't think so. Yeah, because so Tn is the value. Tn actually includes all the value that x1 to xn takes. Like we want to evaluate the joint probability for, say, any setting of x1 to xn. And this theory just tells us, if you want to evaluate, it gives you some structure. And we just look into the structure, and the structure tells us, okay, we can view this joint probability as a marginalization with respect to some intermediate latent random variable theta. That's the idea. And of course, I mean, if you really observe some particular values or settings, if you want to compute posterior distribution, that's actually another calculation procedure. Okay, so if we take a closer look of this integral, right? So we can view this f essentially is a cumulative density function of this latent random variable theta, right? So we can further rewrite the integral regarding theta as a product over all the n random variables, right? So in each for each term in the product, it is theta to the power of xn. Xn is a binary; it's either 1 or 0. So it's theta to the power of xn, 1 minus theta to the power of 1 minus xn. Well, of course, you can just merge all the terms. That means you just sum up over xn, you will end up with this theta to the power of tn, and 1 minus theta to the power of n minus tn. So we decompose this integrand with respect to n is just to show that this term inside the product actually is a Bernoulli likelihood. Okay? It's just a Bernoulli likelihood. And the theta essentially controls this Bernoulli likelihood, or in other words, is a parameter of this likelihood. And plus, because theta itself comes from a prior distribution where the cumulative density function is f. So the whole integral can be viewed, okay, I have some theta, first generate theta, and then given theta, I generate each value of x1, 2, 3 to xn, and then just marginalize out theta. This is what this integral reflects. And definitive theory further tells us the cumulative density for theta, or in other words, it tells us what does theta represent. Theta actually is the limit of average of those random variables. So if you pick any finite n, you take the average of first n random variables in your sequence, you know it's a random variable. And if you take a limit, that means you take n goes to infinity, it's still a random variable. Right? And theta actually is this a limited random variable. And its distribution is determined by F. But whatever, the whole structure or result inside definite theory tells us, okay, the joint probability for any finite set of this exchangeable sequence of binary random variables implies a hierarchical sampling process. Okay? So in this hierarchical sampling process, we're going to first sample an intermediate latent random variable theta, okay, from some prior distribution, which are parameterized by F. And then given theta, we sample the value of each x1, x2, x3 to xn, blah, 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 conditionally independent. And each conditional distribution is a Bernoulli distribution. So in this way, the theory justifies Bayesian modeling because it tells you, okay, there indeed exists a latent random variable, and we first assign a prior over this latent random variable to generate its value, right? Given the value of this latent random variable, we generate each value of the variable of interest, x1, x2 to x3, independently. So any questions so far? Okay, hopefully this will give you some kind of insight about why Bayesian modeling is good. And it is not just a philosophy. Actually, in a very widely used assumption, exchangeability, you can justify its existence. Actually, there are some practical models which leverage this to construct models for graph model. As in 2012, in the Neuronix paper, there is one Neuronix paper leverage this definitive theory to generate graphs. And the way they assign this prior is from some Gaussian process, which we're going to discuss in our subsequent lectures. Okay, back to the exchangeability. So I want to emphasize it is a very widely used assumption in Bayesian modeling. It is more flexible than IID, but it's also restrictive because we kind of assume, okay, if you arbitrarily permute the values, right, those random variables can take, you shouldn't change the joint probability. Right? This is still kind of restrictive, we have to admit, but you know, if you want to make your model more efficient, right, you always have to incorporate some simplified assumption. If you don't make any assumption, well, you usually cannot make your computation easier, make your learning faster, and so on. So exchangeability. So here are a few examples which is based upon the exchangeability. Very classical and popular models like latent derivative allocation, right, which is kind of a very hot topic models about 10 years ago or 15 years ago. And mixed membership stochastic block models, which trying to discover the groups overlapping communities from the graphs or networks, and random function pairs for exchangeable arrays with applications on graph and relation data. And actually, yeah, I want to add a few more examples. If we have a chance, we talk about non-parametric Bayesian modeling, in-depth non-parametric Bayesian non-parametrics. You see that exchangeability takes a key role in modeling sparse data, meaning that, for example, like actually, although we say, okay, this is time for big data, but actually the data is big, but it's not dense in most cases. Like, for example, you have a 2 million or 1 billion Facebook users, but actually the connections between those users, like friendships, although the absolute amount is large or huge, but as compared to all possible interactions, all possible friendships, it is still very, very sparse. Like, for example, if you have 1 million users, right? Suppose you have 1 million friendships. It sounds large, right? But consider if all possible, every pair of users have friendship, you have 1 million by 1 million, 1 million by 1 million, right? But you only have 1 million actual friendships. That means it's still very, very sparse. And if you want to construct an expressive Bayesian prior to capture such structure, sparse structure, like in this Facebook friendships graphs, you have to carefully design the exchangeability. If you, for example, if you assume, if you model arrays, if you model this graph as arrays, and you assume the array is exchangeable, then the prior will generate a dense graphs. But if you assume the edges are exchangeable, plus some particular random process to generate those nodes, you can see that the edges are sparse. So this is really interesting. I mean, if you apply exchangeability at different places, it gives you totally different properties. Okay, so those are up to now we have discussed all the I think which is all the important fundamental knowledge we should know to begin with detailed probabilistic learning models. So to summarize, what you need to know is the fundamental modeling choices in Bayesian and frequentist point of view. Right? What's their key differences? And what is the uninformative prior? Right? What's the most of uninformative prior? So don't get confused about this name, uninformative. Actually, uninformative prior does not mean no informative. Right? It's actually still a little bit informative, but we want to reduce the information as much as possible. So what are the shift invariance, skew invariance in likelihood, how to derive the corresponding uninformative prior? What is Jeffrey's prior, right? So what's the benefit of Jeffrey prior? We know that it's kind of like a arbitrary translation invariance. And what's the assumption of exchangeability, right? What's the difference between the exchangeability assumption and ID assumption, right? And also definite theory. And we don't need to know how this definite theory is proved. We're not mathematicians, but we need to understand what the insight the definite theory reveals. Okay. So now, oops. Sorry, I need to hide this again. Now let us talk about generalized linear models. Okay. So far, I have saying a bunch of things, right? Matrix vector derivatives, MLE principle, MAP principle, convex conjugate, information theory, basic concepts of information theory like entropy, KL divergence, mutual information, and so on, right? And on top of that, we also introduced the basic ideas about probability, right? What is probability space, random variable? What's the definition of expectation variance? What is the exponential family? What's the property of exponential family, right? And exchangeability, definite theory. We'll also talk about a bunch of commonly used distributions. We introduced the concept of conjugate prior, uninformative prior, right? So those, as we mentioned, right, those are just fundamental things, right? Those are kind of like building materials for advanced or commonly used probabilistic models, like generalized linear models, graphical models, Bayesian neural networks, Gaussian processes, and so on. And from now on, we're gonna talk about those models. And correspondingly, when we introduce the models, when we're given this data, we want to estimate model parameters, right? In the Bayesian framework, that amounts to computing the posterior distribution of those parameters of interest, or just give a point estimation, or mix type of inference. Part of the parameters we just want a point estimate. Part of parameters we want posterior distributions, right? That actually we need to address to achieve that goal, we need to talk about different inference methods, right? We'll talk about what is Markov chain Monte Carlo sampling, right? So this is actually the well, I see this method can give you some kind of guarantee, asymptotic guarantee, right? But it's very, very slow. In many cases, just impractical. Then we talk about some biased yet much more efficient techniques called variational inference, message passing, Laplace approximation, and so on. So in our following or subsequent lectures, our discussion will kind of be interleaving introduction of different Bayesian models and also the computational techniques. Well, inference is a synonym of model estimation or training. So yeah, that's a kind of like, I think the term in machine learning is kind of messy. So training is equivalent to inference, is equivalent to learning, is equivalent to calibration, whatever. So the same thing, but for probability guys, they love the word inference, because they will, okay, I have this model, right? I have this model to generate data. I'm kind of given this data, I'm going to infer the unknown parameters. That's where they call it. But other people will just call, okay, training. I want to identify the model parameters, so I call it training. Some people will say, okay, this is an estimation. And some mechanical guy will say, okay, this is a model calibration. But they're all the same thing. Okay. So our next stage, right? We're going to discuss several important and widely used probabilistic models and their general framework. We're going to discuss efficient posterior inference algorithm, and we will start with the generalized linear models. But here, I want to emphasize, we say it's generalized linear models, but it's not necessarily really linear, meaning that we kind of have some linear structure in the whole model framework, but the model itself can be highly, highly nonlinear, can be very complicated. So I'll explain why. So we'll talk about two tasks, right? If you want to construct linear models, models with linear structure to do the regression task and to do the classification task, what kind of probabilistic framework we're going to use, right? And then we're gonna summarize them into a more general framework, which is referred to as the generalized linear models. Okay, we're gonna first talk about the regression task. So regression task, as the name suggested, we assume our output is some continuous value. That is called regression. And our linear models here, meaning that we assume some kind of basis functions. Those basis functions can be linear or arbitrary nonlinear. So we just do a linear combination of those basis functions. That's where the linear structure lies in. So because the basis function itself can be highly nonlinear, so the whole model can still be highly nonlinear. For example, neural network is essentially a linear model with nonlinear basis functions. So we're going to introduce a very straightforward formulation of linear models with like general nonlinear basis functions. We'll talk about their issue through one example. Like if you use polynomial basis, you easily see the overfitting issue. And to address this overfitting issue, a common used strategy is called regularization. We'll talk about what is regularization, right? And then we'll talk about the corresponding Bayesian version, which is called Bayesian linear regression. And upon that, we'll talk about what is predictive distribution. So the predictive distribution actually is kind of an automatic goal of Bayesian guy achieves. This is totally different from the frequency point of view, because if you want to do the point estimation, there won't be any predictive distribution. And finally, we'll talk about what is empirical base. Right? And as we mentioned, predictive distribution is some kind of ideal thing we want to get, right? But we have to compromise on practice, because predictive distribution in most cases don't have any closed form. We have to sacrifice something. Right? We have to make some coarse assumption, and then this kind of compromise is usually referred to as empirical base. Okay. So we're gonna start with the simplest model for linear regression, right? So suppose our input is just a set of features, right? Denoted by this vector x, and we model the output as a function of x and some another vector w, and the form is just a linear function in terms of x. So w0 plus w1 x1 plus w2 x2 until wd xd. Well, we assume you have d features, right? And w0 is usually referred to as the bias term. So I believe everyone has seen this form before. Right? And x, is a vector of these d features. So the limitation here is that, okay, this straightforward model can only capture the linear relationship between the input feature and the output y, right? So to allow nonlinear modeling, right, a very common use trick is that, okay, I'm gonna do some nonlinear transformations of the original features. So suppose I do m transformations, I give m basis functions. So, and then I just do a linear combination of these m nonlinear basis functions. I get my output, right? In this way, we still preserve this easy to deal with linear structure, but because of these nonlinear basis functions, we almost can model arbitrary nonlinear relationship between the input x and output y. That's the idea. Right? So, and here I want to emphasize that each basis function will have the input as the original feature vector, but output is just a real value r. Okay. So the basis function is flexible to use, right? You can use any nonlinear mapping over the input variables, right? So here I give an example. For example, you can define each basis function as a polynomial if your input is just a scalar, meaning the dimension is 1, right? So we can define your basis as just a polynomial to the x, right? Or you can define a Gaussian form, right? Parameterized by different mean and the variance, or some a sigmoid function, right? Parameterized by this shift mu j and s, right? So you have a lot of choices, right? And if you have a multiple variables, well, your feature mapping can be identity mapping or some sine or cosine mapping or whatever. Okay? So again, through nonlinear basis functions, we can model nonlinear functions while maintaining a linear structure. And here, I just want to mention that neural networks can be viewed as nonlinear basis as well. If we consider a neural network, right? So this is your x, your input x, this is vector, right? They through some like a linear transformation, nonlinear activation, linear transformation, nonlinear activation in the second last layer, right? You can view them as your nonlinear basis. Then we know that for the feed-forward neural network, your final output will be just a linear combination of the output of the second last layer. Right? That's why the neural network is often viewed as a linear function of several nonlinear bases, except that those bases are generated by different components in this neural network. Yeah, each particular basis function. Yes. Yes. Oh, let's just say, okay, yeah, you can view sine xj is still a function of x, right? It is just the whole input is the x vector, but output is only determined by j's element of the vector. Yeah, x. Well, this x vector you can visualize x1 and blah 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 xd, right? You just fit this vector to a basis function to give you a scalar. Well, as to how you're going to define a basis function is totally up to you. But you can choose. You can just choose one element in this x and do some transformation. I mean, this just provides a general framework. It doesn't ask you to define your basis function in this way, the other way. And actually, different definition of basis function are corresponding to different models. Like neural network is they have their own way to define basis functions. Oh yeah. So W0, W1 to Wj, like Wm, big M minus 1, they're all scalars. But you can will like W, this body W, right, consists of those scalars. Right? This is actually consistent with our notation convention, right? We introduced before. Okay, any other question regarding this definition? Okay, so now suppose we have a determine, okay, the set of basis functions. We have m basis functions, right? So we got our model, right, which is linear combination of this m basis function plus a plus parameter W0, right? And assume we have a set of observations, right? For each observation, because this is a regression problem, the observation is continuous, right? So assume given the model parameters, the observation follows a Gaussian distribution. And this is a very common use choice. So we assume the actual observation is corrupted by some Gaussian noise. So that means conditional on your prediction, your actual observation is sampled from Gaussian distribution, and this beta inverse indicates the variance of the noise. Okay. So now suppose we have observed n observations, right? So the likelihood of the all n observations, which we assume ID, right, T1 to Tn, will be just the product of the Gaussian likelihood. Now, we want to conduct maximum likelihood estimation to estimate the model parameters. Here will include W and beta. Right? So again, I want to emphasize that this bolded phi is the vector consists of all the basis function values. So it's phi 0xn to phi big M minus 1 xn. So we index from 0 to m minus 1 in total the m basis functions. So we just take a logarithm log likelihood. We have done this practice before, right? So it's just straightforward. You just take a logarithm of each Gaussian density, and it has this form, right? And so this EDW is actually the summation, half of the summation of the square difference between the actual observation and the prediction, right? A linear function. And then we maximize the likelihood to estimate model parameters. That means we take the gradient of the log likelihood and set the gradient to be 0. That tells us we need to solve this equation. Okay. So, and this equation is actually pretty straightforward to solve. Right? You see that W ML, maximum likelihood estimation, has this form. Right? So here, for convenience, we write the solution of the maximal likelihood estimation in terms of matrix. So here, this big phi, big bold phi is called design matrix. So each row of this phi, okay, each row of this phi is actually the basis functions for a particular example. Okay. So you have a n training example, right? So for each input xn, you have m basis functions. So this consists of one row of this phi matrix, big phi matrix. And it is not hard to see that this summation essentially equals to phi transpose phi, because this phi, this big phi matrix is n by m. That's a good question. It's not necessary to be invertible. If m is smaller than n, yeah, it's not necessary to be invertible.
So what we should do in that situation?
Oh, we're going to talk about it in a minute. Okay, so here I just want everybody to get clear about the notation of phi. So phi is an M matrix where each row corresponds to the basis functions for a particular example. So you can see the first row is the basis functions for the first example. So phi 0, x1, phi 1, x1 to phi m minus 1, x1, right? And similarly, the second row is the basis functions for x2, right? So it is m by m. And now come to the question, right? So what if phi transpose phi is not invertible? Right? So if it is not invertible, then this is not the real inverse. We're gonna use pseudo inverse. It's called a Penrose pseudo inverse. Okay. So it guarantees that, okay, as long as symmetric, it gives you, it always gives you some value. But we don't need to know how this is calculated. So here is the maximum likelihood estimation procedure for the linear regression model. It actually unifies the ordinary linear regression model we have seen before. Like if you don't perform any basis functions, you just use original features, and then this phi becomes your training input matrix. It's the same thing, right? So now we want to look into the problem of this formulation, right? So this formulation itself is kind of powerful because by introducing arbitrary nonlinear basis functions, you actually you are able to estimate any nonlinear functions, right? But it can also bring the overfitting issue. So to illustrate this problem, let us consider a particular type of basis, which is called polynomial basis. So for simplicity, we assume, okay, your input is just a scalar, it's just a number, right? So our bases are just power x to polynomial of x, like x to some particular degree, right? And suppose our first basis is just x, second basis is x power x squared, and third basis x cubic until the mth basis x to the power of m. Okay. And of course, we add intercept or bias term here, right, in our modeling. So this is our whole linear model, and with polynomial basis. This model is also referred to as polynomial regression. Okay. So now, so now it comes a question, right? So how can we choose m? That means what is the highest order we can choose, right, for our polynomial basis? Well, that is the problem. Can we make m to be very small? I mean, how do we choose m? How about just to choose m equals to 1? Or how about choose m equals to 100? Anyone have some thought on this? Mm-hmm. Mm-hmm. Okay. Okay. Yeah.
It's a trade-off between bias and variance, actually. If you consider too small n, then you get a underfitting as a high bias, and if you consider n too large, then you will overfit the data with too large variance.
Yeah. Yeah. I mean, the comments of you two are both very great. Right? So actually, intuitively, we can view like, okay, if m is too small, like m just equals to 1, your model is too simple, right? You kind of underfit data where you couldn't capture the real relationship between the input and output. Right? But if you take m to be too large, your model might be too complicated, right? Suppose you only have 10 points. You use a very complicated model to fit these 10 points. You can imagine the model can be the curve, the function curve you learn can be too much wavy, right? So it will hurt its generalization performance. Right? So we can check from the practice data, right? So they actually verifies our intuition. So here is the case where m you simply take 0. Take 0 means okay, you only have this W0. Right? You have this W0, well, you're gonna, oh, by the way, this green curve is the ground truth, and the blue dots are the observed training data. Right? So you can see that m always equals to 0 is just a one horizontal line. Of course, it's underfit data. It doesn't capture any real relationship, right? And if we increase m to be to 1, right? So now it becomes a line, because the highest order of polynomial is just 1. It is just a linear function. You only have this W0 plus W1 times x, right? Of course, this is still not sufficient. Now, if we keep increasing m, like m equals to 3, we can see that, okay, now it kind of fit data quite well, and the learned function kind of quite aligned with the ground truth. Right? This is something we feel satisfactory. But now let us continue adding m. Right? See, add m to be 9. What can we see? Yeah, we can see that when m is 3, this red curve still has some training error, right? It does not guarantee to go through every training points. But fitting to this degree is good, it's satisfactory. If you keep increasing the degree of highest order of degree of polynomial to m equals to 9, you can see that, okay, it can perfectly fit every training points, right? So the training error is simply 0, but now the price is, your learning curve is it kind of varies wildly, right? It's kind of deviate. It actually deviates much more from the ground truth. So if you want to look at the numerical values of those coefficients, you can see this problem, this overfitting and underfitting problem more clearly, right? So here we list the coefficients of different basis functions when you choose different number of basis functions, right? So you can see when your number of basis functions is relatively small, the coefficients are now crazy, right? The values are now crazy. It's kind of reasonable, right? If you choose m equals to 6, that model has already been quite complicated. And you can see that the coefficient for second order and third order polynomial basis are much larger. Right? So you can imagine if you have such a large coefficient multiplied with a polynomial, right? If you just change a little bit of x, the function values will change drastically. That's why what you have seen that the function y it varies so wildly. If you look at m equals to 9, you can see that most of its coefficients of those polynomials are very, very large. So that's why you can see that if you vary x a little bit, the function values can change a lot. So if we further examine, right, how training error and the testing error varies along the increase of M, you can see a typical curve, right? I think any machine learning course will tell you this, right? So M actually indicates the complexity of your model. Right? So increase the M at the beginning. When you increase the M, both your training and the test errors keep decreasing, right? That means, okay, you're gonna better and better feed the data, capture the relationship, and make and generalize. Wow. Right? However, after you model complexity goes beyond to some degree, you can keep feeding data better and better, but at the same time, the generalization performance gets worse, right? So how to address this problem? At least from the coefficients table we have seen, right? I mean, for numerical reasons, we don't want the weights from growing too big, right? If we have some polynomial components, its coefficients is too large. We know that when x changes a little bit, the function value varies very widely. So you can expect that it won't generalize well, right? Because the ground truth won't have such wild behavior. Right? So, so from a computational perspective, right, we don't want weights to be too large. Right? We encourage weights to decay toward zero unless supported by the data. Right? So if the data tells you, okay, I must have a fifth order polynomial or sixth order polynomial, okay, I can let the weights to be non-zero. Otherwise, I hope I can shrink the weights to be small and to be, like in the ideal case, to be even to zero. How can we do that? A commonly used idea is called regularization. So here is the loss over the training data, which measures how well you fit the training data. But to avoid you use too complicated model to overfit the training data, I'm gonna penalize over complex model. Then I add a regularizer. Regularizer is in charge of penalizing over complicated models. In our case, that means I want to the weights of those polynomials to be as small as possible, unless the data says you must have a larger weights. So here lambda indicates the regularization strength. Of course, in practice, you have to manually select lambda, say by cross validation, whatever. So the form of this data loss, for example, a common choice is just a square error. It evaluates how difference between the observed output and your prediction. Right? And a common use the regularizer is just this, half of the square norm of W transpose W. So why is this valid, right? Why is this this is doing well? Right? Remember, in our case, we want to shrink the weights, right? We don't want the weights to be so large. So if we minimize this whole regularized loss, the larger the weight, the larger the second term as well. Right? So of course, I want to minimize this. Right? So even you increase the W, making this square loss decrease, but at the same time you increase the regularizer, that's not good. Right? So you're gonna find some trade-off to ensure that your weight values are not too large. So if we minimize this regularized loss, right? This is called regularized least square. Right? If we minimize this regular loss, meaning that we set gradient to be zero. Right? So if you solve that problem, you get your maximum likelihood estimation. But here we add some regularizer. you see the optimal weight has this form. And but your maximal likelihood estimation is phi transpose phi inverse phi transpose t. And the regularized least square, the solution is a lambda I plus phi transpose phi inverse phi transpose t. So what's the difference here? Anyone? Yes. Right. So as you just mentioned, right? So what if phi transpose phi not invertible? Well, yeah. So the benefit is here. So although in theory, well, if it is not invertible, it is low rank, I can compute some Penrose inverse, right? The pseudo inverse. But I can tell you, the pseudo inverse will give very, very large skews in the inverse. So you multiply the second term, it will give you large values on the estimation. But now, if add this regularizer, that means you add some diagonal matrix to this phi transpose phi. Right? It guarantees the whole matrix now is positive definite. And take inverse, it will give you a much more stable and reasonable value. And correspondingly, your final W, the skew will be quite reasonable. It won't be as crazy as this. That just, I mean, we just explained why this regularization takes effect from the computation perspective. So now, if we add this regularizer, we can just compare the learned weights. Suppose we still take m equals to 9, right? Meaning that I use 9 polynomial basis functions, right? The first column corresponds to no regularization because logarithm lambda is minus infinity simply means lambda is 0, right? So these are just a copy of the coefficients from previous table, right? However, if you choose different regularization strengths, you can see the regularization effect is very, very apparent, right? So when logarithm lambda is minus 18, so you can imagine lambda itself is very, very small, right? But it has already largely reduced the skew of the learned weights. Of course, this might not be enough because those values are still quite large. But if you take lambda simply equals to 1, that means logarithm lambda is 0, right? So you can see that a lot of coefficients are close to 0. Okay? So the relative larger coefficients are corresponding to those polynomials are really needed. Okay? The data select them. So if we take a look at the polynomial regression with different choice of the regularization strengths, you can see the effect, right? So now, even you take m equals to 9, right? If you add a mild regularization, it can make your learned curve much better. But of course, if you take lambda equals to 1, right? It is called over-regularization. You make most of your coefficients too small, right? You only leave the first component, which is dominant, right? So it gives you some curve look like a line. So of course, the natural question will be, oh, how do we choose lambda? And I mean, then you have to select them based on your application. A common used method is to do the cross validation. But here, I introduced this just to give you a sense how the overfitting comes from and what's the commonly used strategy to address the overfitting. And we haven't yet linked it to the Bayesian model. Okay? So here, I give you a general form of the regularizer. Okay? So in the general form, right, we can take the power of the absolute value of each weight in our summation. Right? So if Q goes to 2, then we go back to our quadratic regularizer we just used to illustrate the idea. Right? But Q can be even smaller. If Q is 1, it is known as lasso. It's very, very common used the sparse regression techniques where lasso if you apply Q equals to 1, this regularizer can truncate many components, their weights to be directly to be 0. This is some kind of guaranteed. If your Q is equals to 2, it can only make your coefficients to be approximately 0, like 0.01, 0.02. It won't give you exact 0. But if you use Q equals to 1, many coefficients or weight here will be directly truncated to 0. This is a known property, but we're not going to talk about why. And you can even make Q smaller, like Q smaller than 1. And Q smaller than 1 can give you even sparser result. And when Q goes to 0, this is actually some kind of correspond to the combinatorial search of those weights. In some literature, especially in electrical engineering, if you use Q equals to 0, this is called pursuit matching. If you have some base, you consider you're dealing with some signals, and those signals can be decomposed by several Fourier bases, right? You want to pick up those useful components. They use so-called pursuit matching algorithm. Q equal to 0 just tells you you want to directly prune some components.
You're counting how many are there or not.
Yes. Yeah. But you use this power to, although 0 to the power of 0 is not valid here.
Would it be possible that the weight is a random variable?
Yeah, that's something we're going to discuss right now. So we have discussed so far is just upon estimation. Yeah, that's a good question. In many applications, we would prefer sparse models, especially you have a large number of bases. Like suppose you only have 100 examples, but you have 10,000 bases. Right? And that can easily lead to overfitting. So I want to just pick up a few really interested and powerful bases to represent our model. Then we're going to prefer only kind of basis selection issue, a basis selection problem. But in other cases, like you don't have like strong motivation to prune basis, you might don't need to truncate the coefficients basis direct to 0. You just want to control the weight value not to be too large. Otherwise, it will make your prediction very unstable. Okay. Oh. Oh, it's just a training observation. Like the output, right? If you measure, given this input xn, what is the output? You have observed. Okay, so now let us link this commonly used strategy to the Bayesian framework. Right? So in the Bayesian framework, we know that we don't treat the weights as just a point. Right? We treat the weights as some random variables. So we want to assign the prior over those weights, right? So, but how do we incorporate the regularization effect? Right? So, as later we'll see that those regularizer corresponding to a specific prior of the weights. So, for example, if we take Q equals to 2, right? This is just the W transpose W, right? So actually, if you take exponential of minus W transpose W, this just equivalent to saying that W follows a Gaussian prior. Right? So if you view the whole objective or loss as some logarithm of joint probability, right? So you minimize this loss, that means you maximize their negative values, right? And then you take EXP to recover the joint probability. Well, this part, if you take Q equals to 2, becomes W transpose W negative and EXP, right? So that's actually a Gaussian. Does it make sense? Okay. Forgive my joining. Let me erase them. Right? So the connection to Bayesian is as follows. So this is a whole regularized loss function, right? And we want to minimize. Right? So let us view this loss function as logarithms of some joint probability, and we want to maximize the joint probability, right? That means we need to take minus sign of this loss. Okay, so we know that okay, my log joint probability is this minus regularized loss. Right? So now if I want to recover my joint probability, I just take exp to the whole negative loss, right? So, well, the first part, their exponential correspond to Gaussian likelihood. Right? So the second part, the exponential to the minus this guy will correspond to different prior. If you Q equals to 2, that is W transpose W, right? So it actually corresponds to a Gaussian prior over W. Right? If Q equals to 1, later we'll talk about that corresponds to so-called Laplace prior. Does it make sense? Right? Just associated with the it's exponential form. Right? If Q equals to 2, well, you know, if Gaussian, if this guy follows a standard Gaussian, right? You will see that its density is proportional to exp to the power of minus W transpose W, right? So it's consistent with here. So now let us just look at Q, the case of Q equals to 2, right? So in the Bayesian world, that means we assign a prior over the weights, right? And in general, we can assume, okay, the prior mean is M0 and the covariance is S0, although in practice, M0 is often said to be 0 and S0 is often said to be just the identity matrix. But here we just talk about the general setting, right? And then given W, right, we generate the actual observation T from another Gaussian distribution, right? So the mean will be our prediction. So phi here is the design matrix. And phi transpose W, and we have some noise variance beta inverse. Right? So now we combine the prior with the likelihood. We can calculate the posterior distribution. Right? Given the actual observations of the output, what is the distribution of our model parameters W? This is a pretty straightforward to calculate using the completing the square trick we discussed before. It's really easy to get that. So you will see the posterior mean we denoted by Mn and posterior covariance matrix denoted by Sn in this form. Okay. So Sn inverse equals to the prior covariance inverse plus this beta and design matrix transpose design matrix, and Mn is Sn times this guy. So if we take a simple choice, like we set M0 here, M0 equals to 0, and S0 equals to alpha inverse I, right? So just some alpha controls how the prior variance for each weight, right? And you still use, and then your posterior distribution will be simplified in this form. Here is M and Sn. I mean, you just substitute M0 for 0, S0 for alpha inverse I. You get this. I'm not gonna do this. It's actually straightforward, right? But here we want to use this example to showcase, compare with the prior. What does posterior distribution tells us? We consider two variables, like your W vector only consists of two elements, W0 and W1. So that means your X is just a scalar. Right? because yeah, your x is just a scalar. Because and y will equals to w0 plus w1 x. And here we don't assume any nonlinear basis functions. It's just the naive linear regression case, right? So x, the input is just a scalar. And here is the prior distribution over w0 and w1. So x-axis represents w0, y-axis represents w1. So this color indicates the value of the prior density. So the brighter the value, the larger, the brighter the color, the larger the value. So you can see that because this prior is centered is a Gaussian distribution centered at 0, right? So you can see that at this place you have the largest density, right? So the far away you are from the mean, the smaller the density value is, right? And here is actually means that because we assume y is w0 plus w1x, right? And w0 and w1 are both random variables. If you use the prior distribution to sample w, right? For each particular sample of w, you form a prediction function of y in terms of x, right? So because the prior is quite wide, right? It's quite flat and quite wide. You have many choices of w. So you just random sample a bunch of w. For each particular w, you got a function relationship between y and x, which are essential lines. You can see those lines are quite widespread, right? It can be any kinds of lines, right? And with different slopes, with different intercepts. Yes, like in the very first row, those w's are sampled from the prior distribution. The prior distribution is represented here, which is just a Gaussian distribution controlled by a standard Gaussian distribution controlled by some variance alpha inverse I. Right? So you can see because this prior is quite flat, right? You have a lot of choices of w, right? W can be here, can be here, can be here, can be here. So different w correspond different lines, right? Because the prior is quite wide, quite flat, so you can view that the corresponding function relationship between y and x can be versatile, right? The lines can overspread, I mean, can go spread the whole space, right? So now, suppose we observe one data point, right? And then here, this blue circle is actually the observation. And we can immediately apply this form to compute the posterior distribution of the weights, right? So you can see that the posterior distribution is much different from the prior, right? First, we can see that, okay, the high density region is shrunk much, right? Because you observe some data information. Data information indicates where these weights are, so it won't be as flat as before. It's now much more concentrated than the prior. Then if we use the current posterior distribution to sample the weights and see how those weights are constructing the corresponding function relationship between y and x, you can see the range of those lines are shrink as well, right? It is much narrower. It's not as spread as before. Why? Because the data information tells us that the weights are more likely to be surrounding in this region. The corresponding, the relationship between y and x are more informative than before. And this part just tells you the likelihood. And it just tells you that how this x is observation, right? It just tells you if you view likelihood as a function of W1, W0, how those likelihood value varies. And this white dot is the ground truth value of W0 and W1. So you can see that when you take W0, W1 to be the ground truth, namely this white cross, the likelihood value is relatively large, but it's not the largest. The reason is because we add some random noises to generate observation. That's why it gave you quite a large likelihood value in terms of W0 and W1, but it won't give you the largest because there are some noises to generate the observation. So if we further observe the second data point, right, we can see that, I mean, by applying the posterior distribution, the formula to calculate the posterior distribution again, we see that the posterior distribution of weights is further shrunk, right? And that means, given 2 points, we're even more sure about the range of W0 and W1. Okay? So the high density region is further shrunk. And correspondingly, if you use this posterior distribution to generate samples of weights, and then look at the corresponding function relationship between y and x, those lines are further narrow, right? The range. That means we got more and more certain about the relationship between y and x. And also we can see that when we sample weights from those posterior, those relationship between y and x are quite consistent with the observations. So if we keep adding points, right? Suppose we have observed 20 points, and then we apply our formula to compute the posterior distribution. You can see this is the posterior distribution. And this posterior distribution tells us we're very, very sure about where is the ground truth, but not totally sure because only observed 20 points. Okay. But we can make our range, which correspond to high density regions of the weights, to be quite small. Right? And correspondingly, if we use this posterior to sample the weights and look at the corresponding function relationship between y and x, we can see that all those lines are kind of aligned, right, or overlapping, and all those lines are quite consistent with the observation. Those blue circles. And as we mentioned before, right, if you keep adding points, we talk about there's a Bayesian version of the law of large numbers, right? At the limit, suppose you have an infinite number of points, your distribution, your posterior distribution is gonna concentrate it on this ground truth, right? With no variance. And that means you don't have this orange circle anymore. But that's just a limit. But for the final data, you always have some uncertainty. So you're looking at some posterior distribution rather than just the point estimate. So hopefully this can give you some sense like how the Bayesian inference, when you add more and more points, the posterior distribution tells you how our uncertainty about model parameters is kept being shrunk, and but at the same time we still see some uncertainty on those parameters, which is represented in the posterior distribution. This one? The likelihood figure. Okay. This is the likelihood, right? So this is a Gaussian likelihood, right? So I'm gonna omit this, right? So once you have observed data point, your x is fixed. So this is a function of W0 and W1. The likelihood figure just tells you this. How, if you vary W0 and W1, given this particular observation, how the likelihood changes. And that's why you can see that in all the data points, likelihood in terms of the W0 and W1, they all have like a high likelihood value for the ground truth, this Y cross Y, because it is ground truth, right? But it won't be exact. It won't be the maximum because when we generate the data, remember it is we add some Gaussian noise. Right? It's not like completely match the actual prediction. There are some kind of random corruption from noise. That's why the likelihood will be quite large at the ground truth value of W0, W1, but it won't be the maximum always. Yes, exactly. Each individual point. Yeah. Yeah, hopefully, I mean, this visualization, we introduced this visualization is just to give us a sense, right? How Bayesian people view the model, the training problem. We not only look at if your estimation of W0, W1 is more and more close to the ground truth, this Y cross. We also look at the whole distribution. So you can view that the whole distribution is get concentrated, more and more concentrated. That means, okay, your uncertainty about model parameters is smaller and smaller with more and more data incorporated. But we still have some uncertainty. With that posterior distribution, we can quantify those uncertainty. Does that make sense? Yeah, I mean, this is just a figure from the PRML book. And we're gonna give the link, which is on the page number. If you still feel like uncomfortable with that, just look at the illustration of that page. You'll get, I mean, more detailed understanding of that. But it's not. But this just help you to enjoy the flavor of Bayesian, actually. Yeah. Okay, so in general, like, as we mentioned, like, if we assign our weights a Gaussian prior, it corresponds to quadratic regularization, right? If you set our Q equals to 1, we just mentioned it corresponds to Laplace prior, right? And for arbitrary Q, right? For arbitrary power of Q, and the prior of W is given in this form. And this guy is just it's a normalization term. Right? If you want to make it a valid prior, you need to ensure that the integral over the domain is 1. Right? So this guy just comes from the normalizer. Okay. Yeah, I guess we can stop here today, and we're gonna finish our linear model in the next lecture.